In X-ray micro-CT, a sample is being rotated between an X-ray source and an X-ray detector, while many radiographies are being recorded. Using these radiographies, slices through the sample are reconstructed, which, stacked on top of each other, yield a virtual 3D volume of the sample representing its external and internal morphology. The radiation physics group performs research on nearly all aspects of the X-ray micro-CT technique. My name is Luc Van Hoorebeke, and together with my colleagues Mathieu Boone and Jan Aelterman, I will give you an overview of our activities. The CT research of the radiation physics group has its roots in the second half of the 1990s, when it was operating the UHENT 15 MeV linear electron accelerator. At this LINAC, a fully operational, tunable monochromatic X-ray source was realized in 1996 by an international team. At this X-ray source, the team succeeded in high-energy K-edge imaging, which was also the start of the activities of the radiation physics group in tomographic imaging. In parallel, the group became involved in neutron tomography and developed a flexible neutron tomography setup that was used at the ILL and PSI. For the reconstruction of the raw projection data, the radiation physics group started to develop a reconstruction toolkit, which later became the well-known Octopus software package. After a collaboration was started with the Sedimentary Geology and Engineering Geology group, which is today the Progress group, the Radiation Physics group designed and built a novel modular 900 nanometer resolution X-ray CT scanner, which was fully operational in 2006. At the end of the same year, UGCT was founded. One of the first very high resolution scans is shown here, depicting a 450 micrometer sized foraminifera. Following a close collaboration with Woodlab at a new scanner, in 2008 the Radiation Physics Group developed a 400 nanometer resolution nanowood scanner tailored for the wood research of Woodlab, which joins UGCT in 2009. Afterwards, the Hector, Medusa, EMCT and Heracles scanners were developed, obtaining the very performant complementary UGCT scanner fleet. Next to scanner development, the research of the Radiation Physics Group covers nearly all aspects of the X-ray CT imaging chain, including physics and instrumentation, new tomographic reconstruction methods, and 3D and 4D analysis methods. My colleagues will now highlight some of these aspects.
In conventional X-ray imaging, the image contrast relies on differences in X-ray absorption between different materials, like bone and soft tissue in medical imaging. However, at very high resolution systems, the X-ray refraction becomes visible, resulting in an edge enhancement effect, which enables us to visualize very thin structures like the wing of this fly. Another alternative contrast method is dark field imaging. Based on small angle scattering of the X-rays, this modality highlights small features within a certain size range. This property enables researchers to characterize materials with nanoscale features within a much larger scale volume of interest, like battery electrode materials. Together with researchers from ETH Zurich, we investigate this modality with a so-called dual-phase grating interferometer. The same small angle scattering effect is also driving a technique called tachography. This technique enables much higher resolutions than standard X-ray imaging, reaching even 10 nanometers. However, it is currently only available at synchrotron facilities. Using novel instrumentation and in collaboration with several partners from the UK, we have proven it is possible to apply this promising technique at a lab facility. One of the key elements to enable the lab tachography was the X-ray detector. Unlike conventional X-ray cameras, which record only black and white images, a hyperspectral camera was used which records the X-ray energy for every individual photon. In micro-CT, the use of such detectors enables material identification, such as contrast agents in biomedical imaging or specific metals in geology or electronics. In the Radiation Physics Group, we are doing pioneering research on the use of this kind of detectors in micro-CT. In terms of novel sources, we are investigating the potential in micro-CT imaging of a novel compact light source developed by TU Eindhoven. This source, based on inverse Compton scattering, will offer a tunable quasi-monochromatic X-ray beam with a high flux density. As such, this is a compromise solution between conventional, easily accessible lab sources having a limited beam intensity and huge, less accessible synchrotron facilities having extreme brilliance.
At the radiation physics group, we also innovate in the methods used to process the data that our scanners produce. We focus on achieving higher quality. That means higher spatial resolution, higher time resolution, depending on what the scientific question requires. Broadly speaking, we focus on two types of data processing research. The first is the development of new algorithms, where we seek improved ways to process the data, notably by imposing either a data-driven or a hypothesis-driven model of what it is that we should be imaging. The second type is the combining of multiple sensors data, where we add complementary information to a given micro-CT dataset. Let me give you a few examples. Whenever a research question involves a dynamic process, we find that imaging such process can lead to severe imaging artifacts. This is because standard micro-CT algorithms are designed for static object imaging only. We have therefore researched robust methods for dynamics assessment, like the motion estimation work by our researcher Zaira Manigrasso. Notably, this method produces a model for the motion inside a sample, and we additionally research ways of incorporating such models into our CT reconstruction algorithms. Together, such methods offer an exciting way to mitigate motion artifacts and thus increase the time resolution in dynamic CT. As such, work like that of our researchers, like Dr. Wannes Goethals, is enabling us to create true videos of the dynamics that is going on inside our CT scanners. Now, where new algorithms like this truly shine is when they fuse this data source with other data sources complementary to micro-CT. In one such case, which is the research of our Dr. Benjamin Blijkers from Ghent University's Progress Group, we managed to apply this principle to truly probe into the nanometer scale. Consider this sample. It consists of different particles, some having 150 nanometer sized pores and others having smaller 50 nanometer sized pores. Notice that micro-CT by itself is incapable of resolving into the nanometer scale, as it is impossible to visually distinguish the particles with large pores from the particles with small pores. In our data fusion algorithm, thanks to fusion with dual grating interferometry data, we proved that it is in fact possible to perform high accuracy classification at this nanometer scale.